Welcome everyone. Today we are delving into the duality of cardiac repair. Our goal is to decode the molecular machinery triggered by a myocardial infarction and understand how we can reprogram these pathways to move beyond simple injury suppression toward true engineered regeneration. A myocardial infarction isn't a single event, but a cascade. Occurs in three stages. First one, the ischemic crisis. Here, the ATP depletion leads to immediate membrane rupture. Second, apoptosis versus necrosis. Here, cells face programmed death or catastrophic necrosis. The third one is the alarm bell. Here, necrotic cells release danger-associated molecular patterns, which alert the innate immune system to start the repair process. Left unchecked, this cycle inevitably dictates the progression toward heart failure. The body's response follows a strict clinical architecture. It follows four stages. The first stage is 0 to 3 hours. There neutrophils peak for debris clearance. The second stage is based 1 to 3, where the inflammatory phase dominated by pro-inflammatory among macrophages. In the third stage, it takes 3 to 7 days, called the proliferative phase, where M2 macrophages take over to drive angiogenesis. And the fourth stage takes weeks plus. It is called as the maturation phase, resulting in fibrosis and scar formation. A key player in this timeline is the NLRP3 inflammation. It exists in a state of optimal homeostasis. While we typically view it as a target for suppression, complete inhibition often fails in clinical trials. This is because low-level baseline inflammatory signaling actually acts as a vital cardioprotective primer. Total suppression strips away this survival signaling, leading to pathological damage just as overactivation does. Not all components of the inflammasome are created equal. The first one, NLRP3, deleting this abolishes baseline ischemia preconditioning. The second one, ASC, knocking this out preserves some preconditioning but impacts other survival pathways. And the third is caspase-1. Inhibition only helps in cases of mild ischemia. The takeaway is that deleting a single component does not mimic deleting the entire complex. Each has independent critical functions. This diagram illustrates the signaling paradox. Baseline NLRP3 expression intrinsically regulates the risk and safe signaling pathways, which are essential for cell survival. Total deletion suppresses the survival mechanism, essentially leaving the heart defenseless during the critical reperfusion phase following an injury. The lost in translation trap for existing therapies has been blunt systemic inhibition. The path forward is selective modulation. We must uncouple the detrimental pyroptosis from the beneficial baseline survival signaling. The goal is to disarm the hyperactivated complex while maintaining its protective baseline functions. The second case study is the Notch pathway, an evolutionarily conserved communication system. Post MI, it acts as the master conductor of repair, dictating cell fate and maintaining tissue homeostasis. Notch operates via a spatiotemporal switch. In early phase, it drives M1 macrophages for aggressive debris clearance. In late phase, it pivots the microenvironmental toward M2 macrophages to support tissue repair. Crucially, suppressing Notch early reduces inflammation, but suppressing it late halts the healing process entirely. Successful notch signaling has two vital outcomes. The first, angiogenesis. It intersects with VEGF to dictate how vessel branch and capillaries form. In second, regeneration. It crosstalks with the hippo or YAP pathway to trigger adult cardiomyocytes to re-enter the cell cycle, briefly reopening a developmental window for a new cell growth. However, Notch also has a dark side. While it is required to build the initial patch over an infarct, overactivation hyperdrives fibrosis and vascular stiffening. Left unmodulated, Notch constructs a stiff, non-compliant scar that eventually leads to heart failure. When we compare these two toolkits, NLRP3 is triggered by DAMPs and ATP to manage early survival versus cell death. Notch is triggered by ligands like JAG1 to determine cell fate and angiogenesis. Both share a biological paradox. They are essential for repair, but their overactivation or systemic inhibition leads to clinical failure. This master synthesis map shows how these pathways are interconnected. Altering a single node like Notch1 or NLRP3 cascades through the entire system. Blunt single-target interventions fail because they ignore this dense spatio-temporal crosstalk. We are moving from pharmacological on-off switches to biological volume control. We want to turn notch volume up for targeted angiogenesis. Turn PGF-B volume down to prevent stiff scares. Keep NLRP3 volume maintained at baseline for protection. Caspase-1 volume should be muted. Systemic delivery is becoming obsolete. The future of cardiac repair lies in advanced delivery mechanisms. Instead of blunt IV drips, we will use targeted nanoparticles and localized hydrogel microrods to deliver JAGD1 or VEGF directly where needed. By leveraging gene editing and nanotechnology, we can actively reprogram the cellular blueprint from within the damaged tissue, finally achieving true regeneration. Thank you for watching this video.